Imagine standing at a bustling railway junction. The air hums with anticipation. The ground vibrates faintly as a distant train approaches. You see these incredible machines, steel behemoths, gliding smoothly over tracks, signals flashing their silent commands, points switching with powerful, deliberate movements. It's all part of this meticulously choreographed ballet of engineering.
It really is quite something to watch.
But what ensures that every single movement in this complex dance, every decision made by the system, is not just efficient, allowing trains to flow seamlessly, but profoundly, undeniably safe, especially when we're talking about the physical, mechanical components, those tangible pieces of steel and iron that are constantly moving, bearing immense loads, and interacting directly with the tracks and the trains themselves.
That's the critical question, absolutely.
Yeah. Today, we're taking a deep dive into that exact critical question. We're going to explore the fascinating, often unseen world of railway mechanical signaling. Our mission is to, unpack how we achieve system assurance for these crucial, tangible systems, the nuts, bolts, levers, and gears that underpin railway safety, and how we precisely measure their performance levels to guarantee that safety day in and day out. And this isn't just some academic exercise about complex machines and engineering marvels. It's ultimately about the safety of countless lives and the seamless, reliable operation of a massive, vital network that keeps our world moving from goods to people.
And that's exactly where system assurance comes into play. What's fascinating here is that system assurance isn't just a technical term or, a checklist.
Yeah.
It's a deeply structured, systematic, and proactive philosophy of how we engineer and operate.
Okay, a philosophy. I like that.
Yeah, think of it as a comprehensive playbook for confidence. It's about implementing the right processes, deploying the right tools, and adopting the right methodologies throughout a product's entire life cycle. This isn't just about its initial design concept on the blueprint, but also its manufacturing, its installation on the tracks, its daily operation in the field, through maintenance, and even its eventual decommissioning. The whole thing.
Right, from cradle to grave, essentially.
Precisely. The core purpose of this approach, simply put, is to build rock-solid confidence in a product's integrity and correctness. And it specifically focuses on 4 absolutely critical pillars, often summarized by the acronym RAMS: reliability, availability, maintainability, and safety.
RAMS. Okay, reliability, availability, maintainability, safety.
That's it. For railway mechanical signaling products, which are, the physical heart of so much safety, system assurance is the foundational framework. It's what ensures that these physical moving parts are not just assembled, but are designed and constructed with all these crucial RAMS factors in mind right from the very first sketch. This proactive, preventative approach is essential for identifying and managing potential risks long before they ever have a chance to become real dangers on the tracks.
So it's about foresight, really, catching problems before they happen.
Exactly. And beyond the undeniable moral obligation we have as engineers and operators to prevent harm and ensure public safety, there are also very strong drivers that mandate this rigorous approach. We're talking about meeting stringent regulatory requirements, adhering to specific national and international safety standards, and ensuring legal compliance.
Right. The legal and regulatory side. Can't ignore that.
You certainly can't. These aren't merely guidelines. They are legal and ethical imperatives designed explicitly to prevent accidents, minimize incidents, and effectively manage overall safety within the vast interconnected railway network.
Okay. Now, you mentioned safety within RAMS. But sometimes we hear about functional safety. Is that the same thing, or is there a distinction we need to understand?
That's a really important question, and yes, there's a nuanced distinction. Safety, in its broader sense, describes a state of being free from unacceptable risk of physical injury or damage. This could be direct injury to people, or indirect damage to property or the environment. Pretty straightforward.
Okay. General freedom from harm.
Right. Functional safety, on the other hand, is a very specific subset of that overall safety. It's the part that relies entirely on a control system or a piece of equipment operating correctly in response to its inputs.
Okay. So it's about the system doing its job correctly for safety.
Exactly. For example, if a railway signaling system is designed to ensure that a train cannot enter a section of track where another train is present, or where the points are not correctly set, then that specific control system must meet very stringent functional safety standards. It's about ensuring the system performs its protective duties exactly as intended every single time, without fail, in response to the operational conditions.
That makes sense. It's the functioning part that's key there. So let's unpack this a little more and talk about what we actually mean by machinery in this context. Because when we say railway mechanical signaling, we're talking about very real physical assemblies that interact directly with the trains and tracks.
We absolutely are.
If you consider the fundamental definition of machinery, it's typically an assembly fitted with some kind of drive system, something that imparts motion, right?
Right. Some energy input causing movement.
It consists of linked parts or components, and crucially, at least one of those parts moves. And all of these individual pieces are joined together, working in concert for a specific application.
That's a good working definition.
So when we apply that definition to railway signaling, we're picturing the actual moving components right there on the tracks, or maybe in the signal box. Think about the imposing heavy levers in a traditional signal box that used to physically move points and signals through a complex network of rods and wires.
Oh yeah, the classic single box image. Lots of physical effort involved there.
Definitely. Or picture the robust routing systems running alongside the track, connecting those levers to the actual point mechanisms or the specialized mechanisms that mechanically lock a set of points in place, ensuring they can't shift while a train passes over them.
Those point locks are absolutely critical safety devices.
Critical. Even newer but still largely mechanical point machines that physically switch tracks, or the physical mechanisms within a signal that make the arm drop or the light change, are all part of this machinery. These are the tangible pieces, the physical manifestations of engineering that make the railway system not just function, but most importantly, function safely by dictating train movements.
And this brings us to a fundamental distinction in how we approach and assure safety, depending on the type of technology involved. Many people, especially nowadays, are familiar with EPE systems.
EEPE. Okay, what does that stand for again?
It stands for Electrical, Electronic, and Programmable Electronic Systems. These are absolutely ubiquitous in modern safety applications. Think about the classic clicking sound of electromechanical relays, those trusty workhorses that have been the backbone of signaling logic for decades.
Right, I can almost hear them clicking now.
Or consider more contemporary solid-state electronics, which are circuit boards with no moving parts, and of course microprocessors, which are the sophisticated brains behind incredibly complex modern control systems.
So the electronic side of things.
Exactly. These EEPE systems are found in an astonishing range of safety-critical applications across various industries. You'll see them in emergency shutdown systems in chemical plants, controlling massive turbines, integrated into medical devices, ensuring crane safety on construction sites, and even in guardian interlocking and emergency stopping systems for heavy industrial machinery.
Wow, okay. They're everywhere.
They really are. And indeed, they are integral to cutting-edge modern railway signaling systems, including highly advanced technologies like moving block train signaling, where trains continuously calculate safe braking distances based on real-time data communicated wirelessly.
Very sophisticated stuff.
Very. Now here's the crucial difference in their failure characteristics, which shapes our entire approach to safety. For EPE systems, the dominant failure mode is characterized by what we call a constant failure rate. We refer to these as random failures.
Constant failure rate, random failures. What does that actually mean in practice?
Well, imagine a brand new light bulb. It can fail at any point during its useful life, right? It might burn out tomorrow or it might last for years. It doesn't necessarily get old in the traditional sense. It just suddenly stops working due to some inherent, often unpredictable flaw or perhaps a sudden electrical stress.
So it's not like it gradually dims until it fails. It just pops.
Pretty much. This randomness of failure, where the likelihood of failure doesn't significantly change over its operational life, is a key characteristic of EPE systems. And it's absolutely fundamental to how we assess their safety and predict their reliability.
That's a perfect way to put it, the unpredictable constant failure rate of electronics. But now, let's step off the abstract circuit board and back onto the tracks, because the real world of railway mechanics poses a completely different yet equally critical challenge to safety.
It certainly does.
This is precisely why non-EPE systems, which are purely mechanical, hydraulic, or pneumatic in nature, are so unique. They simply don't behave the same way.
Not at all.
In the railway world, we have countless concrete examples of these. Think about mechanical points, locks, those robust physical devices that ensure a set of track points cannot move unless explicitly commanded and safely released.
Absolutely vital. Pure mechanics doing a crucial job.
Or consider the various types of point machines. Some are still air-operated, using pneumatic pressure. Others are hydraulic, employing fluid power. And of course, countless older, purely mechanical types are still in use globally, relying on linkages and livers.
A real mix of technologies, but often relying on physical force.
Exactly. Even seemingly simple things like physical relays, push buttons that you manually depress, or limit switches that physically open or close a circuit based on a mechanical action, these all fall into this category.
Things you can physically touch and see move.
Right. And beyond railways, you see these types of mechanical systems performing vital safety functions everywhere. Consider an emergency stop button on a factory floor. You physically press it, engaging a mechanical linkage. Or a manual reset lever, a mode selector switch that you physically turn. Or mechanisms designed to prevent unexpected starts on machinery.
Everyday examples of mechanical safety.
What stands out to you, and here's where it gets really interesting, is that their dominant failure mode isn't a constant random event like in electronics. It's fundamentally wear out.
Bingo. That's the key word. Wear out.
These parts don't just randomly stop working. They physically degrade, erode, or wear down over time from cumulative use. And that changes absolutely everything about how we approach their safety assurance, design, and maintenance.
Absolutely everything. When we talk about wear out, we're referring to a very specific and actually quite predictable phase in a product's life cycle. It's the period that typically precedes the actual end of its useful life.
Okay, towards the end of its expected lifespan.
Exactly. And during this phase, unlike the constant failure rate we see with many electronic components, the probability of failure increases significantly over time. The fundamental difference.
So the older it gets, the more likely it is to fail. Seems intuitive for mechanical things.
It is intuitive. With random failures, a component has no memory of its previous use. It could fail today or in 10 years with roughly the same probability. But with wear out, it's all about the cumulative effects of that previous use. Every cycle, every movement, every bit of stress, every vibration, and every environmental exposure adds up. Gradually, the material or component physically degrades and loses its original properties.
Like things just getting worn down from use.
Think of it vividly. Imagine the treads on your car tires. They don't randomly disappear overnight, do they?
No, they definitely wear down over time.
They steadily get thinner and less effective with every mile you drive, eventually reaching a point where they're no longer safe. That's wear out in action. Or consider a railway axle. It experiences millions of stress cycles over its lifetime.
Okay, that makes sense. So how do we model this increasing failure rate? Is it just a straight lineup?
Not usually. While sometimes wear out can be approximated with simpler models, like a normal distribution, the Weibull distribution is actually far more commonly used and remarkably powerful for this.
Weibull distribution. Okay, that sounds a bit technical.
It can be, but the concept is powerful. It's highly versatile. Its shape parameter, often called beta, tells you a story about the failure mode itself. If beta is less than 1, you're looking at infant mortality parts failing early due to manufacturing defects, perhaps.
Like teething problems.
Kind of. If beta equal to 1, it's that constant random failure we discussed for electronics. But when beta is greater than 1, which is typical for mechanical components, that's the definitive signature of wear out, indicating an increasing failure rate over time. This parameter is crucial for precisely predicting the lifespan of mechanical components and when they'll enter this critical wear out phase.
So beta 1 means wear out is the dominant factor.
That's the key indicator. This deep understanding of wear out is precisely why preventive maintenance is so incredibly key for mechanical systems. It's not just about fixing things when they break. It's about scheduling replacements for parts before they even enter that accelerated wear out phase.
Right, getting ahead of the curve.
Precisely. By meticulously doing this, you dramatically improve the overall reliability and safety of the entire system, turning a reactive approach into a proactive one.
What are some common ways these mechanical parts actually wear out?
Oh, there are several common mechanisms, concepts we can all relate to, really. There's fatigue, where constant stress cycles like the repeated bending of a metal arm or the constant vibration on a railway bogie eventually cause microscopic cracks that propagate until the component fails.
Like bending a paper clip back and forth until it snaps.
Exactly like that, just over potentially millions of cycles. Then there's corrosion, where a material steadily loses integrity over time, like the rust you might see on trackside components due to relentless exposure to harsh weather and moisture.
Yeah, rust is a big enemy outdoors.
A huge one. Then there's physical wear, where surfaces abrade or protective coatings are lost due to friction, evident in the polished surfaces of switch rails, where train wheels constantly grind against the steel, eventually leading to play or misalignment.
So just grinding down over time.
Right. Even less obvious factors like thermal cycling, the constant expansion and contraction from daily temperature swings cause stress. And at a microscopic level, phenomena like electromigration or radiation can alter materials, contributing to their degradation over time. All these things contribute.
Wow, okay, so lots of ways for mechanical things to degrade. And this difference in failure mode wear out versus random must impact how we measure reliability, right? You mentioned constant failure rates don't apply.
Absolutely. This difference has a huge impact on how we measure failure. Standard metrics like mean time between failures, or MTBF, and failures per million hours, or FPMH, which are based on the assumption of a constant failure rate, simply don't apply once a component enters its wear-out phase. They lose their meaning.
So using MTBF for a wearing part is misleading.
Highly misleading, yes. Similarly, mean time to failure, or MTTF, only makes sense if that failure rate is constant. So you might have a product theoretically rated for a 10-year MTBF based on its electronic components. But if its mechanical components are under significant stress, they could still show significant signs of wear out and even begin failing in just 2 years.
That's a huge difference. So the mechanical parts could dictate the real lifespan.
Often, yes.
Yeah.
In contrast, electronic components are generally designed so their useful life extends far beyond their intended operational life, precisely to avoid ever reaching that wear-out phase in the first place.
Ah, they design the wear out of the expected operational life?
Generally, yes. However, even within electronics, power electronics can be an exception because they often operate under much higher stresses, more heat, more current, making them more susceptible to wear out, and thus requiring preventive replacement, much like mechanical parts.
Okay, so power electronics are a bit of a special case there. So if MTBF and ATTF don't quite fit the bill for mechanical parts once they start wearing out, how do we actually estimate their failure rates with any real precision?
That's the million-dollar question, isn't it?
It feels like it. This is where tools like Weibull analysis become absolutely indispensable for mechanical products. Since these components inherently don't have a constant failure rate, they age, they degrade, they wear. Weibull analysis allows us to make truly meaningful and accurate average failure rate estimates over their lifespan.
Okay, so Weibull helps model that changing failure rate.
Exactly. The underlying principle here is quite intuitive yet profound. Failure often happens when the stress on a component actually exceeds its strength. Think about a simple bolt. It has a certain inherent strength. But if you apply too much stress to it, or if that stress cycles repeatedly over time, its effective strength diminishes until it breaks.
Stress versus strength makes sense.
So predicting reliability really boils down to predicting the probability of that critical event that the applied stress will eventually overcome the component's diminishing strength.
A probabilistic approach.
Right. In practical application, we utilize specific factors derived from Weibull analysis, such as the Weibull shape parameter, which you just described, telling us about wear out, and something called the characteristic life.
Characteristic life. What's that exactly?
This characteristic life isn't when all parts fail. It's a specific point in time where about 63.2% of a population of those components would have failed. It's a statistical benchmark.
Okay, 63.2%. That sounds oddly specific. Is there a reason for that number?
It comes from the mathematics of the Weibull distribution, specifically when the time equals the characteristic life parameter, eta, and assuming a shape parameter, beta of 1, it relates to the exponential distribution's reliability function. But the key is it's a standard reference point. We combine these parameters, shape and characteristic life, with a carefully planned maintenance interval. This helps us estimate an average failure rate for a component, assuming it's regularly restored to an as good as new condition during scheduled preventative maintenance.
So the maintenance schedule is baked into the calculation.
It has to be. Let's consider a compelling example. Imagine a ball bearing, a small but critical mechanical part found in many railway components, like a point machine motor.
Okay, a ball bearing.
Let's say this particular bearing has a Weibull shape parameter of 1.3, indicating wear out.
Beta greater than 1 checks out.
And a characteristic life of 50,000 hours. Now, if this bearing is scheduled for preventative maintenance replacement every 10 years, its actual failure rate can fluctuate quite a bit over that decade as it wears. However, the average failure rate for a population of these bearings, considering that 10-year replacement cycle, is estimated to be around 20 failures per million hours, FPMH.
20 FPMH with a 10-year replacement. Okay.
But here's the kicker, the truly fascinating part. If you decide to replace that exact same bearing more frequently, say every 2 years, as part of a more aggressive maintenance plan, What do you think happens to that average failure rate?
Well, you're replacing it long before it gets near its wear-out phase, so the average rate should drop significantly, right?
Significantly is right. It drops all the way down to about 14 FPMH.
Wow, from 20 down to 14 just by changing the maintenance interval from 10 years to 2.
Exactly. So the clear takeaway here, and it's a vital one for railway engineers, is that your maintenance strategy directly impacts the average failure rate for mechanical components. This is a stark contrast to the largely constant rate failures we typically see in electronic components, where changing a light bulb more often doesn't necessarily reduce its inherent random failure rate.
That's a really powerful illustration. Maintenance isn't just fixing things, it's actively managing reliability for mechanical parts.
Precisely. And by understanding these calculated average component failure rates, we can then do something really powerful for complex systems. We can estimate the overall average failure rate for an entire mechanical system by simply summing up the average rates of its individual critical parts. This allows engineers to design incredibly reliable mechanical systems by strategically planning not just their design, but their long-term maintenance.
That makes a lot of sense. Aggregating those managed component failure rates gives you a system view. So that's a perfect lead-in to clarifying some of those reliability metrics, specifically MTBF, MTTF, and introducing a new one that's absolutely crucial for mechanical systems, the B10 rating.
B10, okay, haven't heard that one as much.
Right. So let's quickly recap. As we discussed, MTBF, or mean time between failures, is primarily used for repairable systems where the failure rate is assumed to be constant, often following an exponential distribution.
Constant rate, repairable systems. Got it.
In this context, the MTBF represents the point in time where there's about a 63.2% chance of that component having failed. It's a widely used metric, but again, its applicability is tied to that assumption of a constant failure rate.
Okay.
Then there's MTTF, or mean time to failure. This is similar, but applies specifically to non-repairable products or systems items that, once they fail, are simply discarded rather than repaired.
Non-repairable, time to first failure. Okay.
It represents the average time until the first failure occurs within a population of these items.
Right.
So if you have a component that once it fails, it's thrown away, you're typically looking at its MTTF.
Right.
However, for mechanical products, given their inherent wear-out characteristics, we need a different, more relevant, and practical measure of reliability. This is where the B10 rating comes in, and it's a game changer.
Okay, B10. What does the B stand for? And the 10?
The B refers to the bearing life calculation method it originated from, but now it's used more broadly. The 10 is the key part. The B10 rating represents the time at which only 10% of a given product population is expected to have failed due to wear.
Only 10% failed. That's much earlier than the 63.2% for MTBF or characteristic life.
Much earlier. What that means, crucially, is that there's a 90% chance of survival for the remaining products in that population at the B10 point. This is a much more conservative and, frankly, more practical measure for mechanical systems because it gives you a much clearer, much earlier picture of when a significant portion of your components might start failing due to their normal wear patterns.
So it's an early warning indicator for wear out.
Exactly. You're not waiting for 63.2% to fail, which would mean most of your components have already gone. You're looking at the point where just 10% have failed, which is a much earlier, more actionable indicator for preventive maintenance.
That makes a lot of practical sense for maintenance planning.
It really does. There's even an important relationship often assumed in the standards for mechanical safety. The mean time to dangerous failure, or MTTFD, for mechanical products, is frequently approximated as 10 times their B10D.
Okay, wait. MTTFD is 10 times B10D. What's the ad mean there?
The D stands for dangerous. So B10D refers specifically to the number of cycles or the amount of time at which 10% of components are expected to fail to danger, meaning a wrong side failure, or a failure that could directly lead to a hazardous situation, such as point switching incorrectly.
Ah, so B10D is specifically about dangerous failures.
Correct. And T10D is simply the time, rather than cycles, until 10% of the tested samples fail dangerously. So the B10 rating, especially B10T, provides a much more direct, intuitive, and ultimately proactive understanding of mechanical product reliability, especially when safety is paramount, allowing engineers to intervene long before widespread failures occur.
That's really useful. B10D as a key metric for mechanical safety. So we've firmly established that electronics and mechanics fail fundamentally differently. Random versus wear out.
That's the core takeaway so far.
This distinction leads us directly to why we need a different, tailored measure of safety performance for mechanical systems. For our EPE systems, we've traditionally used something called safety integrity level, or SIL.
SIL, yeah. Very well known in safety engineering.
It's a widely known and respected concept in many industries, specifically developed for electronic and programmable systems to quantify their safety performance, essentially, how reliable their safety functions are at preventing dangerous failures.
A measure of risk reduction for electronic safety functions.
Right. But here's where it gets really interesting, and it's a critical point for any engineer working in this field. The SIL concept cannot be applied to purely mechanical, hydraulic, or pneumatic systems.
Cannot. That's a strong statement.
It is, and it's explicit. It's not just an informal guideline. Major international standards like IEC 61508 and the railway-specific EN 50129 explicitly state this. You simply cannot slap a SIL rating on a mechanical point lock and consider your safety assessment complete.
So trying to assign a SIL to a purely mechanical device is just wrong, according to the standard.
Fundamentally inappropriate, yes. The very nature of their failure modes that wear out, we just explored in such detail, makes SIL an inappropriate measure. The assumptions behind SIL, primarily constant failure rates, just don't hold true for mechanical degradation.
The math and the physics just don't align.
Exactly. This is precisely why we need a different, appropriate, and specifically designed standard. And this is where ISO 13849 steps in, introducing the concept of performance level, or PL.
PL. Okay, so PL is the mechanical equivalent of SIL, conceptually speaking.
Conceptually, yes, in that it measures safety performance, but it's derived very differently. So what exactly is a performance level? It's essentially a rigorous measure of how well a safety-related part of a control system, often abbreviated as SRPCS, that's safety-related parts of control system.
SRPCS, got it.
How well that part can perform its intended safety function under foreseeable conditions. In essence, it tells you how much risk reduction a particular safety system can actually achieve. It's a direct, quantifiable measure of its reliability in a safety context.
So higher PL means more reliable safety function.
Exactly. A higher PL means a much higher probability that the safety function will perform as intended when needed, or conversely, a much lower probability of a failure to danger, which is often referred to as a wrong side failure rate in railway terms.
Lower chance of failing unsafely.
Right. The PL is divided into 5 distinct levels, ranging from A through E, represents the highest safety reliability, making it suitable for the very highest levels of risk, where the consequences of failure would be most severe.
PLA, B, C, D, E, with E being the highest integrity, and that ties directly into how we actually assign a performance level rating to a mechanical system. What's crucial to understand, and you hinted at this earlier, is that you can only assign a PL rating after a thorough, meticulous risk analysis has been performed.
Risk analysis first, then PL. You can't just pick one out of a hat.
Absolutely not. It's essentially meaningless to try and assign one beforehand because the PL is a direct output of understanding the specific risk you're trying to mitigate and the degree of safety integrity required to reduce that risk to an acceptable level.
So what are the steps involved in getting to that PL?
The process involves a series of logical, systematic steps for any engineering team. First, you identify the specific hazard. For instance, in a railway context, that might be a train collision at a junction or a derailment.
Okay, define the bad thing that could happen.
Right. Next, you identify all the potential hazardous events that could arise from that hazard. Perhaps the point switching incorrectly while a train is on them, or a signal failing to display the correct aspect.
How could that hazard actually occur?
Exactly. Then, you critically determine if any risk reduction is actually necessary. Is the inherent risk unacceptable as it stands? If it is, you then figure out precisely how to achieve that risk reduction and then identify the specific safety functions that are needed to accomplish it.
What job does the safety system need to do?
Precisely. Only then, finally, can you determine the appropriate performance level for each of those identified safety functions.
That sounds logical, but how do you actually make that final determination? How do you choose between PLC or PLD, for example?
That's where a practical, widely used tool comes in, called the risk graph approach. This method systematically considers 3 main factors to guide you to the appropriate PL, almost like navigating a decision tree.
A risk graph. Okay, what are the factors?
First, there's the severity of injury. S. This is a cold, hard look at the potential harm to people. S1 indicates a slight, usually reversible injury, perhaps a minor cut or bruise. F2, on the other hand, means severe, irreversible injury, including death.
S1 slight, S2 severe. Pretty clear cut.
For a railway system, an S2 scenario is typically what we're working to prevent, as consequences can be catastrophic.
Understood. What's next?
Second, we consider the frequency and/or duration of exposure to the hazard F. How often are people or the system exposed to this specific risk, or for how long are they exposed? F1 would be for rare to often exposure, or short durations, perhaps maintenance personnel occasionally working near a hazard. F2 indicates frequent to continuous exposure or long durations, such as passengers constantly traveling through a complex junction.
F1 infrequent short, F2 frequent continuous.
Okay. And third, the possibility of hazardous prevention or damage limiting, P. If something goes wrong, if the hazard occurs, is it possible for a person to prevent the hazardous event from escalating or limit the resulting damage?
Right.
P1 means prevention is possible under certain conditions. Perhaps there's an audible warning and enough time to react. P2 means it's hardly possible to prevent it, meaning an instantaneous event with little or no time for human intervention.
P1 possible to avoid, P2 hardly possible.
Right. So by meticulously assessing these three factors, severity, S, frequency, F, and possibility of prevention, P, you follow a specific path on the risk graph. Each combination of S, F, and P leads you to a specific required performance level, from A to E.
Like a flow chart leading to the required PL.
Exactly. This method provides a very objective and transparent way for engineers to determine the necessary safety integrity for a mechanical system, ensuring it's appropriately robust for the identified risks.
That objectivity seems really important. Now, you mentioned SIL earlier. How does PL compare? Is PLE the same as SIL3 or SIL4?
That's a common question. While PL and SIL are distinct and developed for different types of systems, there's a loose comparison possible based on the probability of dangerous hardware failures per hour. It's interesting to note that the highest integrity level typically achievable for a mechanical product using this framework, performance level E, is generally considered comparable to SL3.
PLE is comparable to SL3. Why not SL4?
It's largely because, in the context of these standards like ISO 13849, mechanical failures are generally not assumed to directly lead to catastrophic outcomes involving the death of many people, which would typically push an electronic system towards needing SL4 integrity. Mechanical failures are often more localized or might lead to a system shutdown or blockage, which, while serious, is often considered less severe in terms of mass consequence than, say, a high-consequence failure of a complex electronic safety controller managing multiple trains.
I see. The assumed consequence level for mechanical failures tends to cap the requirement around a SIL3 equivalent. Okay. Once that performance level has been assigned through the rigorous risk analysis, the next absolutely crucial step for engineers is validating it. How do you prove the system actually achieves, say, PLD?
Right. Assigning it is one thing, proving it is another. Remember, PLs are specifically defined in terms of the probability of dangerous failure per hour, or PFHD.
PFHD, probability of dangerous failure per hour.
Yep. This PFHD for a given safety function isn't just a single isolated number. It's a complex calculation that's influenced by several critical factors inherent within the system's design and operation.
Okay, what factors feed into that PFHD calculation?
First, there's the system architecture. This is all about how the safety-related control circuit is designed to behave when a fault occurs. How fault-tolerant is it? Engineers use powerful analytical tools like hardware failure modes and effects analysis, or FMEA.
FMEA. We hear that acronym a lot in engineering.
We do, and for good reason. It isn't just a checklist. It's a rigorous systematic thought experiment. For a mechanical point machine, an FMEA might meticulously map out what happens if a specific gear tooth wears down, or if a critical spring loses its tension. Does it fail in a safe way, perhaps just locking the points, or does the design inherently prevent a dangerous outcome?
Thinking through all the ways it could break and what happens next.
Precisely. This detailed analysis then directly informs architectural choices, like designing redundant mechanical linkages, meaning you have a backup physical path, or implementing fail-safe braking mechanisms that prevent uncontrolled movement. Different architectures are categorized, often as Category B, 1, 2, 3, or 4 in ISO 13849, based on their fault tolerance capabilities and how they handle single or multiple failures. Higher categories generally allow for higher PLs.
So the structure of the safety system matters hugely. What else?
Next, we look at diagnostic coverage, DC. This tells us how well the system can detect its own faults. It's about the extent of built-in monitoring mechanisms.
Can it tell if something is wrong with itself?
Basically, yes. Does the system have sensors or internal checks that can spot a mechanical failure almost immediately, like a broken rod or a misaligned lever? Or could a fault go unnoticed for a period, potentially leading to an unsafe condition? Higher diagnostic coverage means the system is better at self-monitoring, which significantly enhances its overall safety performance because it reduces the undetected dangerous failure rate.
Makes sense. Better self-checking means safer operation. What's next?
Then there's the reliability of components, specifically their mean time to dangerous failure, or MTTFD. For mechanical parts, as we discussed earlier, this directly depends on the B10D value, the number of cycles, or the amount of time until 10% of components fail dangerously.
Ah, the B10D value feeds directly into the PL calculation through MTTFD.
It does. The more reliable your individual components are and the longer their B10D values, the higher your overall system reliability and thus the higher the PL you can potentially achieve.
So quality components are fundamental.
Absolutely. Another crucial factor, especially if you have redundant systems, meaning you've built in backup components or parallel paths to enhance safety, is the protection against common cause failures, CCF.
Common cause failures, what does that mean?
This is about ensuring that a single event, like a power surge, a specific environmental factor like flooding or extreme vibration or even a maintenance error, doesn't knock out all of your redundant safety channels simultaneously. If you have two identical point locks side by side, a flood might disable both.
Right, the redundancy doesn't help if the same thing takes out both systems.
Exactly. So diverse designs where redundant systems operate on different principles, maybe one electric, one hydraulic, and physical separation, where they are located far apart, are often used to mitigate CCF risks. We need to quantify how well we're protected against these.
Okay, so architecture, diagnostics, component reliability, common cause failures, anything else?
Yes. One more major factor is the system's protection against systematic errors. These are fundamental faults that are actually built into the design itself, rather than being random hardware failures or wear out.
Faults in the design itself, how do those happen?
They might stem from an error in the specification, a design oversight, a calculation mistake, or even a misunderstanding of requirements. They're often much harder to find and fix because they're inherent to the logic or the physical design. Rigorous design processes, independent verification, thorough validation testing, and quality management systems are absolutely key to preventing these systematic errors from manifesting in the final product.
So it's not just about the hardware failing, but making sure the design was right in the first place.
Precisely. Beyond these quantitative factors that contribute to the PFHD calculation, there are other equally important considerations for validating the PL. This includes the overall quality of the design process itself, ensuring it follows best practices and incorporates lessons learned. The operating stress the system will endure, which directly impacts wear and degradation. The environmental conditions, things like extreme temperature, humidity, and dust, which can significantly accelerate mechanical degradation.
Right, real-world conditions.
And of course, established, well-adhered to operational and maintenance procedures, making sure the system is used and cared for correctly throughout its life. All these elements collectively contribute to the ultimate validation of the assigned performance level, providing confidence in its real-world safety.
It's a very comprehensive picture you need to build.
It really is.
Yeah.
With that comprehensive understanding in mind, let's get a better overview of the specific standard that guides all of this. EN ISO 13849.
ISO 13849. That's the key standard for PL, right?
It is. This European standard, often harmonized globally, is absolutely central for mechanical engineers working on safety-critical machinery and their control systems. It's specifically designed to support them in ensuring the safety compliance of mechanical products.
And it covers more than just purely mechanical.
Yes, it has broad applicability across various technologies, electrical, hydraulic, pneumatic, or purely mechanical components. It's particularly valuable and often referenced for products developed with electromechanical technology, effectively bridging the gap between purely mechanical components and more complex electronic control elements that might interact with them.
Okay, so it's quite versatile. What kind of design strategies does it promote for safety?
EN ISO 13849 describes well-established design strategies explicitly aimed at minimizing what we call failure to danger situations. These strategies are quite intuitive and focus on a layered, robust approach to safety. First, there's the goal to avoid faults in the first place.
Make it strong, make it reliable.
Exactly. Designing for inherent reliability and robustness from day one. You want to make components incredibly strong and resilient, minimizing the intrinsic chance of them ever failing. Second, it's about being able to detect faults if they do occur, despite your best efforts.
Build in monitoring and testing.
Right. Implementing robust monitoring and testing mechanisms to quickly identify when a component isn't performing as expected, like a sensor indicating a lever hasn't reached its intended position. And third, and perhaps most interesting from a design perspective, It's about being able to tolerate faults.
Tolerate faults. How does that work mechanically?
This is where concepts like redundancy and diversity in design come in, allowing the system to continue functioning safely even if one part fails. Think of having two separate mechanical locking mechanisms for a set of points, perhaps operating slightly differently. So if one jams or breaks, the other can still ensure the points remain locked and prevent a hazardous event.
So backups and different ways of doing the same safety job.
Exactly. This layered approach, avoid, detect, tolerate, ensures that safety is built in, monitored, and maintained even in the presence of a fault.
Avoid, detect, tolerate. That's a neat summary.
It is. The ultimate output, the tangible goal of applying this standard, is to determine and then achieve the appropriate performance level, be it PLA, B, C, D, or E, for the specific safety functions embedded within that mechanical product. It's a comprehensive framework that guides engineers from initial risk assessment through design and implementation all the way through to validation and ongoing maintenance, ensuring these systems meet their critical safety obligations throughout their entire operational life.
And all that rigorous design, detailed analysis, and meticulous validation ultimately needs to be proven, not just asserted, right? You can't just say, we achieved PLD.
Absolutely not. You have to demonstrate it. This is where the assurance argument comes in, and it typically takes the form of comprehensive technical documentation.
The paperwork.
Well, yes, but it's crucial paperwork. For mechanical products, this documentation isn't just bureaucratic process or a dusty file. It's the concrete, undeniable proof of safety. It's your ultimate declaration of compliance and safety integrity.
Okay, fair enough. It's the evidence trail.
Exactly. The core objective of this extensive technical document is to provide all the necessary evidence, logical arguments, and detailed information to demonstrate beyond a doubt that the product will operate safely and reliably. This means showing that it performs exactly as intended under specified conditions and that it meets all the defined RAMS requirements we discussed earlier. It's reliability, availability, maintainability, and safety characteristics.
So it ties back to RAMS.
It does. Crucially, it specifically shows that the product's safety functions, with their assigned performance level, fully comply with all the relevant requirements of ISO 13849. It's a formal, traceable declaration of safety integrity that can be scrutinized by regulators and independent assessors.
So what kind of information must be included in this critical document? It sounds like it would be pretty detailed.
It is extensive because you're literally building an irrefutable legal and technical case for safety. You need to clearly document the specific safety function or functions that the system provides. For example, the system safety function is to prevent point movement while a train occupies the section.
Define the job.
Yes. For each of those functions, you'll detail its precise characteristics, such as the required response time or the force it needs to apply. You also need to define the exact boundaries of the safety-related parts. Where do the safety-critical mechanical components begin and end within the larger system assembly? This prevents ambiguity.
Scope it clearly.
Environmental conditions are paramount too. With temperature ranges, humidity levels, vibration profiles, or dust exposure is the system designed to operate within. If it's for outdoor trackside use, these factors are vital for predicting wear and ensuring appropriate design.
Define the operating environment.
Absolutely. And of course, the determined performance level, PL, and the safety architecture category or category selected must be explicitly stated. You'll also include key reliability parameters like the calculated mean time to dangerous failure, MTTFD for its components, the diagnostic coverage, DC, detailing how faults are detected, measures taken against common cause failures, CCF, explaining redundancy or diversity, and the expected mission time or design life for the product.
All the numbers and parameters we discussed earlier.
All the key ones, yes. Beyond the quantitative numbers, the documentation must detail the measures taken to prevent systematic failures, those fundamental design flaws. You'll list all potential safety-relevant faults that were considered during design and analysis, and just as importantly, provide a clear, logical justification for any faults that were excluded from consideration, explaining why they were deemed irrelevant or already mitigated by other means.
Justify what you didn't consider too. Interesting.
It shows thoroughness. The overall design rationale must be clearly presented, explaining the underlying thought process behind the critical safety design choices. Why did you choose this mechanism over that one? And finally, measures against any reasonably foreseeable misuse of the system need to be documented, demonstrating that even improper or unintentional use has been considered and mitigated where possible.
Thinking about how people might misuse it too.
You have to. This entire package forms the comprehensive assurance argument that a mechanical railway signaling product is indeed safe, reliable, and fit for purpose, and that engineers have done their utmost to ensure its safe operation. It's the safety case, essentially.
Wow, that's a lot that goes into ensuring these mechanical parts are safe.
It really is. So, to bring this all together and reflect on our deep dive, what we've explored today is how system assurance really provides the essential backbone for safety in railway mechanical signaling. It's that proactive, structured approach that ensures reliability, availability, maintainability, and ultimately safety throughout a product's entire life cycle, from its very conception to its final decommissioning.
The whole life cycle underpinned by RAMS and assurance processes.
Exactly. A key distinction we've emphasized today is the fundamental difference between electronic and programmable electronic EEPE systems and purely mechanical systems. EPE systems primarily experience random failures, almost like a flip of a coin, and are therefore assessed with safety integrity levels, or SO-ELO.
SI for electronics, constant failure rate.
Right. Mechanical systems, on the other hand, are dominated by predictable wear-out failures, a gradual decay over time, and consequently are appropriately assessed with performance levels, or PL, using standards like ISO 13849.
PL for mechanical wear-out failure rate.
Precisely. This isn't just a semantic difference or a matter of choosing different acronyms. It's a profound difference in their inherent failure characteristics that dictates how we must fundamentally design, rigorously test, and meticulously maintain them for safety. It influences everything from material selection to maintenance schedules.
It changes the whole engineering approach.
It really does. The critical role of ISO 13849, particularly EN ISO 13849, is absolutely clear. This standard gives mechanical engineers the precise tools, the methodological framework, and the required structure to design, analyze, and validate the safety of these essential mechanical components. It's about ensuring their reliability and, crucially, preventing dangerous situations by specifically addressing the unique challenges of mechanical wear, degradation, and predictable failure.
The rulebook for mechanical safety integrity.
In essence, yes. And finally, we've highlighted how comprehensive technical documentation isn't just regulatory paperwork or a bureaucratic hurdle. It's the critical assurance argument itself, the tangible, meticulously compiled proof that demonstrates a product meets its stringent safety obligations. It's the culmination of all the analysis, design, and testing, presented in a way that assures regulators, operators, and ultimately the traveling public alike of the product's integrity and safety.
The proof is in the pudding. And the documentation.
You could say that.
Okay, so what does this all mean for the future of railway safety? We've seen this clear fundamental distinction between how we assure electronic and mechanical systems, SIL versus PL. But as railway systems become increasingly integrated and complex, with robust mechanical elements working hand in hand with sophisticated electronic controls, a fascinating and indeed vital question arises for the engineers shaping tomorrow's railways.
Where do we go from here?
Yeah. How might these distinct assurance methodologies, SIL for electronics and PL for mechanics, continue to evolve? Will they become even more specialized, perhaps focusing on increasingly minute aspects of their respective domains? Or might they perhaps even converge in some way to meet the demands of truly hybrid safety-critical systems, where a single vital safety function might rely on an intricate, perfectly synchronized dance between electrical signals, complex algorithms, and physical-mechanical motion?
That interaction point is becoming increasingly common.
It really is. It truly raises an important question about how we ensure holistic end-to-end safety in an increasingly interconnected and technologically advanced railway world. How do we make SIL and PL talk to each other effectively, or do we need something entirely new for these hybrid systems? Something for all of us, especially engineers in the field, to really think about.